All right, let's get started. Get the lights and whatnot adjusted. All right, so let's make sure everybody is clear on the calendar and whatnot, because we are going to have some things happening real soon, so I want everybody to be aware. All right, so number one, you all have your homework due to me today. So if you haven't already done so, here, I'll tell you what, I'll just start a pile right here. Start that there. If you haven't already brought it up, go ahead and do so. Okay, so that's homework 2. Homework 3 is going to be assigned today. It is due on Monday. Now, this is by and large covering stuff that you should be good to go on. So problem 1 is a block shear problem. The only thing I will indicate is make sure that you're clear that there are 2 angles. So make sure you're accounting for those properly. Problem 2 is a design. You're designing a WT shape, specifically a WT7. You've got all the connection parameters and everything right here. You are going to design off of slenderness, and I did give you a little note that if you're just looking at a WT, the RX is actually a little smaller. That's not the same for a W section. It's backwards, so I wanted you all to be aware of that. And then problem 3 is another design problem. You're selecting a channel, but you're also going to go back when it's all said and done and check block shear for this one as well. So all in all, should be pretty straightforward. This is due on Monday. And let me go back to here. So I wanted everybody clear on the schedule. Okay. So let me go ahead and pass this out. Everything's also on Blackboard as well. Now, while we're passing this out, let me also mention something. So I've got here the notebook. I'm going to pass this around. It's got the sign-in sheet, sign in, and then also give it the once-over and make sure you've got everything. If you don't have a handout or a printout, let me know, and I'll provide one. Just put it next to your name. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 6, 7. All right. Okay. Anybody got any questions on the schedule? One other thing I'll point out, we are having our celebration on Friday, February 17th. So I'm going to start having that on the slides just so nobody's ambiguous or not aware. So I want to start putting that up there. Now, for in here, I mentioned this last time, but because our exams, just by the very nature of steel design, because you're having to look a lot of values up in the manual and what have you, I don't want the exam to be a time crunch. I don't want it to be an examination of how fast you can push buttons into this and how fast you can write numbers down. So I'd like to start the exam at 8:30, and as far as I know, nobody in here has an exam before, right? I mentioned that last time. Is everybody good? All right. I said I'd send an email, and then, of course, I forgot. So I'll send an email out to everybody just to be official, because there's still a few folks who haven't gotten here yet today. Sound good? Last announcement, so SAME ASC, they're having their next meeting tomorrow at 6 p.m. in the computer lab up here. There's pizza, and if you want to be involved, maybe get involved with Steel Bridge or something like that, might be worth checking out. All right, that's all I got. Everybody good? Okay. All right, so today what we're going to do is we're going to discuss threaded rod design. Now, I also want to be clear, this is our last topic that's going to be on exam 1. Okay, yes, sir? Well, if you were here, well, if you were here, I'll remember that. All right. We're going to just, like I said, we're going to discuss threaded rods, and this is going to be our last sort of topic that goes on exam 1. But before I get into threaded rods, I do want to take a step back and talk about something that's kind of important. Now, before I get into this, I'm curious how many people have heard of this, heard of the Hyatt Regency collapse. Has anybody heard of this before? Okay, all right. So let me talk a little bit about this event. I hope I turn that on. So this was a collapse of an elevated walkway in the hotel lobby of the Hyatt Regency out in Kansas City. Now, this was a while ago. This happened in the early 80s, but this was a big one in our. I don't mean to start off discussion today with a topic that's somewhat somber, but this is pretty serious stuff. When this failed, it was the worst failure of a structure, and it still is, worst failure of a structure under its design load in U.S. history. Now, you go, well, wait a minute, what about 9/11? What about the Oklahoma City bombing or something like that? Well, yeah, there was a much more people died during those instances, but they weren't under normal operating conditions. This failed under day-to-day normal operating conditions, and over 100 people died. Okay, so this was pretty serious. And ultimately, the failure was the result of a connection-related issue associated with a threaded rod, which is why we're talking about that, talking about this today. So I asked if anybody had heard that, and I see most people said no, but when I showed the picture, I saw a few people may shake their head yes. Is this familiar at all? Okay. All right. This is worth a little more time if you've never heard of this before. So let me sort of set the stage for what happened. So this is a picture showing what it was like before the collapse. Now, like I said, this failure took place within the Hyatt Regency in Kansas City. So this is a pretty big hotel in a pretty major urban area. Now, this hotel, you know, if you've ever been to a big hotel in a big city on a Friday night, it's a party, you know, just about all the time. I mean, there's lots of stuff going on. And what tended to happen in this hotel on the weekends were these sort of like tea party slash, you know, cocktail hour slash, you know, dancing shindigs. And the lobby and the area was pretty packed. So, I mean, like I said, this happened on Friday night, so it was a pretty packed house. Now, so here's an image of the lobby, and what I want you to pay attention to are these skywalks, okay? Now what's going on is we've got this skywalk. We've got one on the second floor and one on the fourth floor. Now, like I said, it's a big area, so it was packed. These skywalks were full, particularly the one on the second floor. You got a bunch of folks here drinking and having a good time. Well, they reached the design load, and what happened was this. So this connection right here on the fourth floor skywalk, you can see this is a zoom in of it. We've got a number of these threaded rods that are threading into this box beam, which was essentially two channels that were welded together. Well, what happened is once they reached a certain load, snapped right through. So what happened was this connection essentially completely failed, as is the case with all the others. Not only did the second floor skywalk fall, but the fourth floor skywalk fell on top of the folks that were on the second floor skywalk. So it was bad, okay? This is what it was like after. Yes, a lot of people lost their lives this day. Now, they did a forensic investigation. They started to, I mean, when 100 people die, a lot of people tend to ask why. So they did a forensic investigation, and they started collecting all the debris, all the samples, and then they you know, interviewed everybody who even touched the project. You know, all the contractors, the engineers, looked at all the drawings, and what happened essentially boils down to the image on the very right. So the image on the right shows the framing detail that I mentioned earlier, and you can look and you can see the difference between how the element was built and how it was actually designed. So the image on the right, the detail on the right, that's how the walkway connection was originally designed. So it was originally designed to be one single threaded rod that hung from the ceiling, and you'd have the fourth floor walkway on it and then the second floor walkway on it. And then that was it. Well, the contractor decided they didn't want to deal with a threaded rod that was that long, so they figured they'd cut it in half, drill another hole, and just go from the roof to the floor, and the fourth to the second, and just have two threaded rods. And I mean, hey, he saved about like $20 on each connection. Good stuff, you know, right? Well, here's the problem with that. Can anybody see what happened? You know, if we look, not really looking at the threaded rod, but looking at the channel, you can see that he definitely changed the load distribution on that channel. I mean, as built, that channel is subjected to a massive amount of shear, right? And look what happened at the very end. I mean, you can see it just ripped right through, okay? So, you know, I mentioned this, I want to say on day 1 or day 2 or something like that, but I remember saying, you know, at the very beginning, I was like, I'm going to mention all this big picture stuff, and then you all are going to forget about it. Because then you're going to be talking about gross areas and net areas and stagger factors and shear lag and block shear, and you're going to miss, hey, what's going on? What are we talking about? This is the type of stuff that we're talking about. I mean, this was a very fundamental design, and I mean, things happened. A lot of people died. It's definitely worth mentioning. Yes, sir. That's a good question. I'm not 100%, but it wasn't long. I mean, it was. I know that this facility was fairly new, and all the contractors and whatnot, they were still practicing and whatnot. So it wasn't that long. Ultimately, I will say that the blame for the event fell pretty squarely on the contractor. I mean, all of the analysis suggested that if the detail had been constructed as designed, you wouldn't have had the issue. The contractor, like I said, figured they save a little bit of money, and there you go. That's what happens. They didn't contact the engineer to check and see if that was right, and then there you go. Yes, sir.
There's just one big threaded rod from the ceiling down to the bottom. How does it like grip a hold of the channels?
Oh, that's a good question. Okay, so what should have happened was this. And I think the easiest way to, maybe the easiest way to explain it is to look right here. So what would have happened is you would have had a single threaded rod, right? And then essentially you would have had a washer and a nut that would have had to fit across the entire bottom, so they'd have to go and slide it up and then screw it in right here. You can kind of see it like right here, but essentially you'd have had a little nut that it would have been resting on. But the issue isn't really, again, the issue with this really wasn't the rod, it was the channel. By changing the connection parameters, they completely changed the load distribution on that channel. I mean, I say channel, but really what they did is they had 2 channels, and they had a sort of a bead of weld running in between them, and that's really what failed, just ripped right through that. Yes, sir?
Why would you ever put more stress or tension or even like bolt on a weld?
What do you, are you talking about just in this?
Because like it shows that the rod is going right through the weld. Why would you ever want to do that?
That's a good question. I'll be honest, normally wouldn't. I mean, if it was me, I probably wouldn't have even done the 2 channels back to back. I would have just used something like a tube. That's honestly, that's what I would have done. And to answer your question, yeah, in most cases you really wouldn't want to do that. Now, let me also say this. This was, and I don't remember the dimensions, but this was most likely designed as what's called a groove weld. And when we talk about welded connections, we're really not going to spend much time talking about groove welds, because by and large, when you design and detail a groove weld, you're really not doing that much designing. You're just filling it with enough weld metal such that the capacity is not governed by the weld metal, it's governed by the metal associated, in this case, with the 2 channels. So basically, you're just, for lack of a better scientific term, you're just welding the heck out of it. And that's essentially what was going on here. They placed so much weld that if it was going to fail, it was really going to fail the channels. And that's really what happened. I mean, you can see here from the forensic investigation that it was the channels that sort of gave out. I mean, it gave out right where the welds were. But to in general, answer your question, yeah, you really don't want to do that. That's a good point, though. Any other questions? This is important stuff. I mean, I don't want anybody in here to feel like, you know, I mean, if you got questions, ask.
I have a question. I have an answer.
You have an answer.
It was open for a year.
Oh, it was open for a year?
Yeah.
I knew it wasn't long. It wasn't long. Because if I remember correctly, they were constructing it throughout the 70s. So.
It opened July 1st, 1990.
Okay. So, It was pretty short. Does anybody else? I mean, this is good stuff. The wonders of the internet, right? Was there a Wikipedia article on it?
Actually, this diagram shows you why it makes it veiled.
Oh yeah, I mean, well, this is a little. This probably isn't as good, but that's the one. That's from the report. So.
But it makes sense that, like, when you split the connection, then it has 2 times the load.
Yeah, because now you have the reaction from the second floor going this way, and then from the fourth floor going like that. So you're literally doubling it up right there. You're changing the load distribution altogether. Over here, it was just bearing. Now it's shear. So it's completely different. But hey, again, contractor saved about $20. Oh well, that too. That's why the contractor made the decision. And honestly, in that bubble of thought, I can see why the contractor would make that decision. But you're changing the design. And you can't do that until you go through and check with the engineer. That's the whole point. Okay? That's the problem.
That contract is not
No. Let's just say their insurance agent was not a fan of them afterwards. Like I said, we live in a litigious society. A lot of lawsuits associated with this. All right. Any other questions? This is good stuff. We definitely have plenty of time. So, all right. I do want to talk about threaded rods, and I do want to discuss how they are designed, because one of the things, let me be clear, threaded rods are very good elements for design. I mean, I don't want you to see Hyatt Regency and go, nobody would ever use a threaded rod. No, that's not the case. Threaded rods are still a very lightweight alternative to a typical tension member. They're lightweight. They're efficient. They are used in a number of instances, and they work very well. They're also incredibly easy to design. I mean, it's not like tension members where we've got to make a boatload of assumptions and we've got to go back and check those assumptions. It's not like that. Threaded rods are pretty simple, and I think after we go through some of the math, I think you'll kind of understand that. So let's talk about threaded rods. First off, let's talk about their availability. Now, when you spec out a threaded rod, I mean, you're speccing it out based on available round bar diameters. Just to give you a quick rule of thumb, typically available bar diameters, typically you're going to go anywhere from 1/4 inch to 1 1/4 inch in 1/8 of an inch increments. So anything like 1/4 inch, 3/8, half, 5/8, 3/4, anything that's in 1/8 of an inch up until about 1 1/4 inch. Then once you get past 1 1/4 inch, it tends to go up in 1/4 inch increments. Like, it's pretty tough to find a 2 3/16 inch diameter round bar, but you could find 2 1/4 pretty easily. Okay, sound reasonable? So when we do our calculations, we're going to get something like, I'll make up a number. We'll get something like the minimum bar diameter is 0.85 inches. So we'll just say round it up and you use something like a 7/8, just to keep it simple. So that's sort of where that's going to come into play. It's just we'll round up and use the next one. I mean, I'm fairly confident that if you all calculate a bar diameter of 0.85 inches, that you can go to a catalog and find the first one that'll work. So that one's pretty simple. To compute the capacity of a threaded rod, it's pretty simple. Okay, so the capacity is the nominal tensile stress times the area. Now, in this case, when I say area, I am not saying diameter of the hole times the thickness. In this case, the area really is pi over 4d squared, because here's the threaded rod, I'm yanking on it, and then samurai sword or lightsaber through the section, and what do I have? A round bar. Okay, so the area is pi over 4d squared. All right, sound good? All right, now what I want everybody to do is I want everybody to open their manuals. I want to turn to this page, because this page is not only relevant for today, but it's going to become a little relevant later. So this is on 16.1-120. So again, this is in that back section of the manual. And it'll be the one on the left. So I'm gonna hang out for a little bit. I'm gonna make sure everybody can find that. Okay. Doing good, doing good, doing good, doing good. And like everybody brought their manual today. All right, that's what I like to see. All right. Okay, there we go. All right, now let's see. So you're going to go way ahead, like your 16.1, and then you're going to go to 120.
Does this page need to be marked?
Good question. Does this page need to have a tab on it? That's debatable, but what I will say is this. If you open up the spec, remember how like Chapter D was the design of tension members? Remember that? Okay, well, we're in Chapter J. Chapter J is the design of members or design of connections. Now, I don't know that you need a tab on this particular table, but I think you do need to be able to find Chapter J pretty quickly. Specifically, J.3. Oh, let me turn it down. Specifically, J.3 or J3. J3 is for bolts. J2 is for welds. So you probably need to be able to just find that section of the manual, because if we started placing tabs on every single one of those tables, we'd have tabs all over the place. So I'll leave it to you where to place a tab, but I'd put something in there. Now, if you notice, I've got the two rows that are on the bottom highlighted, but I do want to look at the rows above, because that's going to become relevant next time when we start talking about bolts. If you notice, you've got Group A07 bolt or A307 bolts, and you've got Group A bolts and Group B bolts. Does everybody see that? Okay. Now we're going to be talking about that next time, but if you'll notice, we've got delineations between the center column, which is nominal tensile strength, and then on the right, which is nominal shear strength. So for most of the connections that we've been looking at are bolts. Do you think our bolts have been experiencing tension or shear? Shear. The bolts have been sheared. So you'll notice, and I know we're sort of jumping across a little bit of different topics, but look at the two rows for Group A, and you'll notice what's the difference between the two rows for Group A. And it's the difference is whether or not the threads are in the shear plane. So in other words, if I've got a bolt and I'm shearing it, am I shearing it through the threads or through the main shank of the bolt? Make sense? And notice how if you're shearing it through the threads, the shear capacity, the nominal shear stress, is smaller, right? For instance, for Group A, the nominal shear stress is 54 KSI if you're going through the threads and 68 KSI if you're not. Make sense? But also, the tensile strength, they didn't change at all, right? Because the tensile strength, the bolt doesn't care whether or not the threads are included or excluded from the shear plane, because it's not in shear, it's in tension, okay? Now, on Wednesday, we're going to care more about what's going on up here, but right now, I want to look at these two rows, which is threaded parts meeting the requirements of Section A3.4, that's just the material spec, when threads are not excluded or are excluded from the shear planes. And what it tells me is it's pretty simple, that the tensile strength is just 75% of FU. Okay, so that's just, if it's not a Group A bolt, if it's not a Group B bolt, it's just 75% of the tensile strength. So pretty simple. Sound good? All right, that's point one. Point two is our phi value. Okay, remember, this is just nominal capacity. We must then adjust it by phi of, in this case, 0.75. So if you notice, the design capacity of a threaded rod is 0.75 squared FUAB. One of those is the phi value, and the other is the reduction for nominal tensile strength. Sound good? Yes, sir?
Yeah, what did they include the mega Pascal SI units for this, even though the whole manual has been given to us?
That's a good question. So the question was, why do we have SI equivalents if the manual is in US units? It's a good question. I'll answer it two ways. Number one, if you go back to, like back in the manual, there's a tab that says miscellaneous, like in the very back. It actually lists SI equivalents of the shapes. So if you wanted, you could do all these calcs in SI. That's point one. You can also download properties. There's a big Excel template, and you can download all the shape databases in SI as well. But one thing you got to be clear about is when you start going into the world of SI, like a lot of things change. Like it's not a W12 by 35. You know, it's like a W300 by 56 or so. I don't know. It's however many millimeters deep it is and how many kilograms per meter the section weighs. But you can do all this in SI. I don't. I just ignore it. But I guess the best answer is because you can. So is that good? Is that fine? Everybody else? So yeah, those numbers in parentheses are just the SI equivalent in megapascals. Okay. So far so good. All right. So we have 0.75 squared FUAB. One of those 0.75s is the phi value. Another is the reduction in capacity for nominal tensile stress. Okay. One of the other things that makes threaded rod design easier is we don't have to check slenderness. Okay. If you go back to slenderness in section D1, here's the section out of the code. Let's just read this out. There is no maximum slenderness limit for members in tension, and we've already discussed that. Technically, the code does not have a slenderness limit. It does say for members designed on the basis of tension, the slenderness ratio L/R preferably should not exceed 300. However, this suggestion does not apply to rods. Okay? Threaded rods are inherently slender. They're meant to be slender. You don't need to worry about applying a slenderness limit to a member that is specifically selected to be slender. You don't have to worry about it. So, so no issue on threaded rods slenderness limits. So because we don't have slenderness limits associated with threaded rods, and because we have a nice, simple expression for capacity, it's pretty simple. We just have to solve. So here's how this works. I know there's a lot of algebra here, but this really isn't that bad. All right, so let me walk you through this. So let's take our time with this. So phi RN is 0.75 squared times FU times AB. Okay? So 0.75, that's 3 over 4, right? 3 over 4 squared, that's going to be 9 over 16. And then the area of a rod, A sub B, is just going to be pi over 4 dB squared. Pi over 4 times diameter squared. So combine everything up, I get that phi RN is 9 pi over 64 times the tensile stress times the diameter squared. Pretty simple, right? Okay. I'm in design mode, so I want to solve for the diameter. So how do I do that? Well, this design capacity has to be greater than or equal to the load, to the factored load. So this design capacity is 9 pi over 64 FU dB squared. That's got to be greater than or equal to the factored load. Rearrange and solve for the diameter. So this FU goes on the bottom, 9 pi goes on the bottom, 64 goes up top. Take the square root. Take out the 64 and the 9, and there you go. That's it. So once you get a factored load, plug and chug. That's it. Simple, right? Really isn't that bad, okay? So I hope when we use this equation, I hope you don't think I'm, pulling the answer out of the hat, like pulling the rabbit out of the hat. This is really pretty straightforward. Just plug and chug, get your diameter. That's it. Any questions? Okay. Then let's do this. So hopefully this example should seem somewhat relevant considering our previous discussion. So we're going to design hangers for that walkway. Okay? So we're going to design ACE-36 threaded rods for a suspended walkway. Now there's some info here that's worth mentioning. So number one, we got a 4.5 inch thick reinforced concrete slab. So help me out. What is the typical unit weight of normal weight reinforced concrete? Say it again. 150 pounds per cubic foot. 150. All right. Now, we've got a walkway that is 6 foot wide. We've got the rods. They're spaced longitudinally at a distance of 20 feet. We also have a live load that is 100 pounds per square foot. It's also already going to be reduced, so we don't have to worry about that. All we have to do is select the rod, so ultimately we're solving for the diameter. Sound good? No. That's a good question. And the answer is no, it is not. So we are going to have to consider that. Sound good? All right. But there's a couple other things that we're going to have to do with the load as well. So let's go through this. So, all right. Now help me out. I'm going to do my best artwork here. I'm not an artist, so bear with me. So we've got Is that good? Is that reasonable? Good enough? So that's 6 foot, okay, because the width of the walkway is 6 foot, okay? Now, ultimately, what we're designing are the rods, but we got one more dimension. Let me do this. So this dimension right here is 4.5 inches. So ultimately, like I said, we're trying to design these, the actual rods, keeping the walkway up. Well, no, but we are doing this, okay? What is the distance? How far apart are they spaced? 20 feet. So it's not a matter of deciding how many they are. It's more about determining, well, what is each individual rod responsible for, okay? And I think you're going to see where I'm going with that here in a second. So far, so good? All right, so we'll just say the walkway sort of goes on forever. Now, what I want to do is I want to look at this in plan view. So let's see, what do we got? We've got sort of that. And somebody made the comment, like I had blue eyes, said, no, your eyes are green. Okay. I'll use green. There we go. Something like that. Do I need like lashes or something? I'm I'm not that good. We're just going to remove that. That's, you know, why don't, you know. I'll go in and edit the video so that that's gone. Of all the things I've done, that's the one. All right. So looking at this in plan view, we've got essentially this thing going on. We've got that, and we'll just say the walkway goes on forever, you know. It just sort of extends in both directions. Oh. I'll do better now. Okay. So what we've got is we've essentially, looking at it in this view, we've got a bunch of rods that are sort of sticking up like that, right? So those are the rods that are supporting the walkway, right? Now, first off, how far apart are these rods spaced? 20 feet. And how wide's that? So if I'm looking at an individual rod, maybe what I ought to be looking at is that individual rod's, there we go, tributary area. Which tributary area for an individual rod, if I just pick any one of them, is just going to be halfway over and halfway over, and again halfway over. So if I'm looking at that rod, that's the tributary area, right? Make sense? So help me out. What is this dimension right here? There we go, 3 feet, and then this one right here, 20 feet. So the tributary area is going to be what? There you go. Pretty straightforward, right? Any questions? Now, let me ask you this. So we've got live load on this rod, right? I think that's the easiest one. How am I going to determine how much live load goes on a particular rod? What is the live load? Let's just go start there. 100 what? PSF. So no, it's not pounds, it's pounds per square foot. It's a pressure, all right? So you tell me, how am I going to determine the force, the load on that rod? Well, ultimately, I'm going to have to factor the load, but what did you say? There you go. It's 100 pounds per square foot applied over a square footage of 60 pounds per square, or 60 square foot. So 100 PSF over 60 square foot, you just multiply the two. So the live load is just just 6 kips. Does that make sense? That one should be pretty simple. All right. Is there anything else that rod has to support, though? That's a good point. It does have to support its own self-weight. Ultimately, though, the actual weight of the rod is somewhat negligible. When we're talking about a rod that's only yay big and maybe, I don't know, 12 foot tall or something like that, it's heavy, but it's in no way, shape, or form comparable to what? The slab. The slab is going to be much heavier. So help me out. I have a unit weight, which is 150 pounds per cubic foot. How am I going to use that? What am I going to do? You tell me. All right. The volume of the concrete. Exactly. We need the unit weight and we need the volume. So let's look at dead load. Now, you're making, hold on. You're making another good point because it's got to be in feet, okay? So let's watch that out. So dead load. All right, so dead load is, okay, remind me, what's our unit weight? 150 pounds per cubic foot. And then you tell me what the dimensions are. How long is that element going to be? There we go. That's an easier way of doing it. Just take the tributary area of 60 square foot times a thickness. And what's the thickness? 4.5 inches. Anybody got a problem with that? So what do we need to do? There we go. And what do we have here? And that's going to be 3375 what? Pounds. I got a second on that? All right. Or 3.375 kips. And I'm using kips because our F sub U we're going to look up is in KSI, right? Now, Mr. Schaffer, now what do we do? There we go. We factor the load. So if I've got a dead load and a live load, I'm just going to keep it simple. How do I factor that? There you go. Mr. Fadiga, though, you are on the money. 1.2. Now, I'm sorry. All right, 1.2 times the dead plus 1.6 times the live, so 1.2 times 3.375 kips plus 1.6 times 6 kips. So what does that come out to be? I heard 13.65, you said? I got a second on that? Here we go. Now, there's that. Let's see, what else do we need? We know that it's A36 steel, right? What does that tell us? Now, continue that. F sub y is... But exactly, if you follow that out, you can look up an F sub y and an F sub u, But for this particular problem, we don't need the F sub y, because for threaded rods, we're just going to say our limit is the F sub TAB, just the fracture. So we need F sub u, which is, no, that's where you got to look it up. There we go. Now that's yield stress. Now hold on, I see a number of people and we're guessing. Now we're guessing because we're not looking it up. So make sure everybody can find that table, right? Table 2-4, yes sir. Okay, now we've mentioned this before, help me out. Think about it like this. If you were designing this threaded rod, and this is a perfect example, and this rod is going to hold up a bunch of people at a tea party, and you don't want that floor to collapse and everybody to die, what would be the most conservative estimate? Say it again. Use the lower one. And we always, yeah, okay, so that, when in doubt, you're always going to go with the lower one. So in this case, so 58 KSI. All right. Everybody else okay with that? Because you know any batch of steel is going to at least meet the 58 KSI. You can't tell me with certainty that it's going to meet 80. You see what I mean? Yes, sir. Why is there a range? That's a great question. It's not that clear without a little bit of background, but the answer is earthquakes. And here's why. So back in the 70s and 80s and all that, I don't want to go too far into this, but back in the 70s and 80s, the steel industry was telling every structural engineer and architect and what have you to resist earthquakes properly, use moment frames. In other words, use those rigid frames as opposed to the ones that are braced, because the perception is that moment frames would allow more movement, which is really an advantageous thing in an earthquake, because more movement and more ductility is more desirable. You want the building to be able to translate as much as possible. You don't want it to be really, really rigid, because really, really rigid indicates a lot of force, and we do our best to try and keep that down as much as possible. So we were telling everybody moment frame, moment frame, moment frame. Now, here's the problem. You go to the steel mill and you pick up a piece of A36 steel, okay? The spec says you must meet, or you must have a tensile stress of at least 58 KSI. And they were meeting it. They were also getting a lot more, okay? They were reaching 60, 70, 80 KSI. Now, the steel mills were like, fine, because when they sell a piece of steel to a fabricator and an engineer specs out that piece of steel for a project, the steel mill was like, well, we know we're meeting the spec because we're getting 58 and more, right? The problem is that by actually getting a larger FU than what we were speccing, the buildings weren't able to withstand as much deformation as we thought they were. There was an earthquake that happened in the early 90s called the Northridge earthquake. And there are all these moment frames all over the place that had failed. And why? We've been telling everybody to use moment frames, and they were fine. And they were designed properly, assuming 58 KSI. And they weren't getting 58 KSI. They were getting 60, 70, 80. So the steel wasn't behaving like they thought they were. So they report that range really to sort of indicate that. Now, I know for your purposes for a threaded rod, it's like, I don't care. I just want to know what number I need to use to size the rod. Well, that's why. Long story, I know, but that's why. Long story, I know, but that's why. All right. That answer your question? Everybody else okay with that? All right. All right. So if we've got a factored load and we have a tensile stress, the threaded rod design is incredibly simple. All we do is this. So for threaded rod design, I think I can fit everything right here. We just do the following. The minimum bar diameter has got to be as follows. 8/3 PU over FU pi. And that's it. Now again, I did not just make up that equation off the top of my head. That's just taking pi over 4d squared our nominal capacity and just solving for D. That's it. So plug and chug. What's PU? And notice how I've got that in kips, because the F sub U that I'm using is 58 KSI. So plug and chug and tell me what that gives you. 0.73. Do I have a second on that? Take your time. All right, so we got a second on that. So 0.73 what? Inches. 0.73 inches. So if you were the designer and you were the one specking out this rod, what would you tell me to buy? Probably about 3/4. Exactly. 3/4 of an inch. So the answer is, and that's a word, right? Probably about. It's an abbreviation. Use a 3/4 inch diameter rod. And that's it. It's really that simple. Yeah, threaded rod design is not too complicated. It's pretty straightforward. What's that? Okay, all right. Now that's a good point, but I want to explore that. Okay, let's be clear. Okay, let's be clear about a couple things. That rod is in actuality only seeing about 9 kips, 9.3 kips, but we're using 13 kips. So we've already bumped the load up 4,000. Then let's also be clear. We're using a phi value of 0.75, so our usable capacity, we've already taken that usable capacity and took 25% off of it. Wait, bump it up to a 1/2 inch? It's a 3. No, I'm serious. I'm sorry, but no, I'm dead serious. We're going.
Save money on welds, put JB weld on it.
What?
Why are you welding a threaded rod?
Not the rod. What? Bump it up to an inch and it'll be fine.
But I also know if you use a 3/4 inch, you'll be just fine too. You've taken the live loads and bumped them up 60%. You've taken the usable capacity. You've actually bumped the capacity down 25% twice, because you took the tensile stress, bumped it down 25%, then you used a phi value of 0.75. So you've done that twice. What?
Let me get this straight. By factoring your load by another 3/4 inch, you can essentially drop part.
That's not what I'm saying. No. This is a good question. All right. Let me say this. All right. To answer your question, this walkway can handle the loads that it's subjected to with a fair amount of uncertainty, assuming that it is in fact a walkway. Okay. I'm not saying this to make a joke, but what you're suggesting is, well, it can handle so much load that we might as well treat it as if it's a parking garage. Okay. If we were doing that, well, we probably wouldn't have designed it for 100 pounds per square foot. We would have designed it for whatever a parking garage is subjected for. What I'm saying is that this walkway is designed to be just that, a walkway. And under its intended use, it's just fine. Okay? All right? We do the same thing for floors in buildings. This room up here was designed to be a classroom, or in this case is where the Dean Suite is, so a bunch of offices. That does not mean turn it into a library. Okay? No, this is an important point, okay? If somebody were to come in and say, no, we're going to take all this and turn it into a full-scale library, well, a structural engineer would then need to come in and evaluate the floor system and say, well, can you really do that? This is a good point, okay? I'm saying under its intended use, it's fine. You're talking about changing the use, and then now that requires further investigation. Yes, sir?
What if it again has a minimum diameter of like 0.78? Where it's so fat, is that a
I-
judgment call or you bump
It's a judgment call. I would bump it up. I would bump it up, honestly. Because it is that one rod being subjected to all that load. Just for me, I would bump it up. And honestly, I mean, there's plenty of engineers out there would say, you know what, a 0.75 inch is fine. Just for my own gut feeling, you know, if it comes back to me, here's the math, and I went up. You know, that's what I would do. Would it be fine if you use 3/4? Yeah, probably would. But I would bump it up. So.
What type of connection do they use, like, on the other end of the block?
You talk about literally, they're just gonna have a hole drilled through and a nut
Yeah,
and a washer, and that's it.
on the very top floor, very top.
The same thing. There's gonna be a hole. There's gonna be a beam. There's gonna be a flange, hole, drilled through. That honestly, which we're gonna talk about, you know, stuff like that later on when we get into things like prying action. We might have some, if we have some time, I'd like to discuss prying action, which is, can the member just hold that tensile force, or is it gonna pry out? That's a discussion in and of itself. So, if we have time, I would like to talk about that. So, yes, sir.
So if you're gonna have the 1.75, I would put up some 7/8 or what is
I'd bump it up to 7/8 because that's probably what's going to be available. But let's also not live in the ivory tower. If my local supplier doesn't have any 7/8 inch, I'll bump it up to the 1 inch. I mean, let's also be clear. There's reality going on too. You know, maybe Huntington Steel doesn't have any 7/8 inch diameter rods. Maybe they've only got 1 inch, and that's what I'm going with. So these are good questions. Anybody else? This is good. I mean, yes, sir. Well, that's what this is. If you want, you can take a 3/4 inch diameter rod and calculate FRN. What you'll find is it's going to be a little bit larger than this. You really don't have to go through and do that, though, because unlike the tension member, there weren't really any assumptions made. You mean, like with the tension member, we were having to assume a thickness, like we just said, oh, let's just take the effective net area and make it about 75% of the gross area. There's a lot of assumptions going into that, and you have to go back and check it. The beauty of a threaded rod design is that that didn't really happen. So whatever you get, the math works out. It's good. I mean, if you want, you can say pi over 4d squared, multiply it times this, multiply it times 0.75 twice. You know, one for the reduction in tensile strengths and one for phi. It'll work. What are you doing that?
Yeah.
Tell me what you get. So remember, you know, that times the area of that times 0.75 twice.
14.41.
There you go, 14.41, and this is 13.65. So, anybody else? All right, that is exam 1, right there. Everything from then on, from today on, is exam 2 and 3 and whatnot. So, exam 2 is going to be on bolted and welded connections, and finals is going to be on columns and beams. So, yeah, so our next topic, we're actually going to look at the bolts and the plate, you know, looking at the plate in a much more localized fashion, not looking at the tension member as a whole, but literally, you know, that little bit of plate right around the bolt holes. Is it strong enough or not? So that comes next. Okay, I'm sorry. Well, most of you are still here, so. All right, that's all I got. I'll see you all on Wednesday. How come nobody stopped me? No.